Any questions before we get started? So we'll probably at least talk about the lab, but I guess we'll finish up our lecture formally. So we had left off on catalysts here. And so catalysts are just substances that affect the rate of the reaction without being consumed. And so you saw that today. So you had the potato catalyst. And the last time you did that reaction, you used potassium iodide as a catalyst for the decomposition of our H2O. I'll put Ki or potato. Water. And so the important thing to note about catalysts is that they provide just a different mechanism, so meaning, right, completely different pathway, and that's also going to affect the activation energy. And so this is a reaction that happens in the atmosphere, and without a catalyst, it's a pretty slow mechanism. And then with a catalyst, so such as like a chloride or something, or a chlorine radical, then that would catalyze the reaction. So kind of thinking of volatile organic chemistry too. So that's why halogens are like the greatest for the environment. And then, so they're not really consumed, so they're just, again, provide a mechanism or a way for the substrate to bind. And then this is kind of, I guess, the ideal situation because it says that they're made or recovered in a later step. And this is not just always the case, so we'll mention a few cases. All right, so looking first at just our reaction diagram. So like we said, catalysts are substances that affect the rate of the reaction without being consumed. And most of the time, at least in chemistry here, we're talking about positive catalysts when we use the term catalyst. It could technically also be used to slow a reaction called a negative catalyst. And then do you remember what that term is in like biology, for instance? What's a negative catalyst called in biology typically?
An enzyme?
So an enzyme would be more like a positive catalyst. So I'll put enzyme. Just inhibitor. You were thinking of like the right. So an inhibitor is just, again, that's the term used in biology, right? Something that kind of gets in the way of it, or maybe binds to the active site as well, and so that would then inhibit or slow down your reaction, but again, not be involved. And so going back to the recovering the catalyst piece, so like I said, that's kind of easier said than done. And so that kind of drives the difference too between these two types of catalysts and when they would be appropriate. So for example, a heterogeneous catalyst, so species are present in different phases. So this is typically easier to kind of work with and separate. And so for example, like your car's catalytic converter is a good example of this. And again, obviously different phases. So the catalytic converter is typically made out of like some sort of platinum metal or contains platinum. And then obviously it's some solid hunk that the gas, right, is passed through. So, right, your gas is passed through, and that helps, of course, reduce the emissions. And so again, if it's in different phases, a heterogeneous catalyst, usually you do have a good chance of recovering that catalyst or using it over and over and over again. You know, like your car catalyst obviously passes gas over and over and over again. And so we could also have a homogeneous catalyst, which all species are present in the same phase. And so this is usually like a liquid reaction, kind of our typical chemistry reaction in some senses. But the problem with a homogeneous catalyst is, of course, once you throw it into your pot, how do you get it back out? And again, right, that's like a lot easier said than done. Especially for these catalysts, they may only have like a certain, it's called a certain percentage of loading. So basically, right, you want to get 100% yield, but you don't need 100% of your catalyst, so it could be like 5 or 10% loading is what it's called, so 5 to 10% kind of your molar ratio of catalyst. But then, like I said, how do you recover such a small amount? That goes into the workup of the reaction, which we won't go into, but that being said, usually the catalyst might get trashed in that case. And so let's pull up a type of catalyst that is a homogeneous catalyst that you can buy. And so I don't know if you've ever heard of these Grubbs catalysts. And so they're pretty famous. So Grubbs and other people who designed it won a Nobel Prize back in the day for it. And so why they won and why they're so wonderful, I guess we'll say, is they're very robust. They can do a lot of this olefin metathesis reaction, so they work a lot of the cases. And then now you can actually buy them as commercially available products. So that's super useful for researchers, and this is literally what the catalyst looks like. So some metal, and it's got this carbene attached to it, some other groups on there, again, other phosphine groups. And okay, that's nice. So again, we just kind of want to appreciate this. And then again, we want to think about how this creates a new pathway. And so we can at least kind of appreciate the reaction that it does. And then again, appreciate how it makes that new mechanism. So if we scroll down, and unfortunately, you don't always get like the best diagrams of this. They kind of do it shorthand. But here's your metal ligand, so that's just to signify whatever catalyst you're using. And so they're just saying how it adds across, and then reductive elimination, do your olefin metathesis, and make your new product here. And so again, right, new pathway, since it's able to bind to the metal and do that transformation versus just trying to get those two things to react. And then looking at it graphically, so again, an uncatalyzed pathway tends to have a higher activation energy, right? That makes sense, since that's usually unfavorable, or maybe it's a high energy transition state. And then again, your catalyzed pathway tends to have your lower activation energy. And then notice how we have like two humps too. So that's typically also what could happen with the catalyst, is it kind of breaks down your reaction into separate steps. Again, kind of thinking about what we just saw in the Grubbs catalyst. So I'm not expecting you to kind of replicate it, but at least just like appreciate that you have a step of where it binds, and then it rearranges and releases. And so again, that's kind of where those different humps come in depending on the process. All right, so that basically sums up lecture. But then I did want to talk about our lab today and kind of go back to Le Chatelier's principle a little bit. Where's Le Chatelier's? So we had looked at Le Chatelier's principle, and again, kind of wordy on the lecture notes. It's just hard to explain it. But it's a lot easier to look at examples. So I'll make a new page. So I'll just say Energy Lab. Chatelier's principle. And so let's just set up our reaction again. So we had this iron 3+ species and our thiocyanate, and we said this was pretty light, yellow, colorless. And then we could react it with the iron thiocyanate, or the thiocyanate, excuse me, to make iron thiocyanate here. And so this, again, complex to make that nice blood red compound, as I think everyone observed. So now let's look at this in terms of what we were supposed to be doing in lab and stressing it. So we had our reference tube. And then, so the first thing we had to do was we added 10 drops of iron nitrate, or add iron nitrate, or iron 3+. And so what did that do to your solution? Did it go darker? Did it go lighter? What do you predict, though, off of this, right? What are you adding when you add iron nitrate? Are you adding reactants or products? What did you say? But so you're not adding iron thiocyanate, though, directly, though, right? But then you probably said product because it went darker, though. But what actually happened? So let's think about this a little better. So, right, we added iron nitrate. So this is really just an iron 3+ source. And then this means that we're adding our reactant, right? And because we've added more reactant, now that caused it to shift to the right, and favor more products, as indicated by the darker solution. So does that kind of make sense? So it goes back to Le Chatelier's principle, right? So we started off, we had a reference tube at equilibrium, right? It was happy. Then we added more reactants to it, but then it had to shift to compensate. And obviously it's still darker, right? Higher concentration than what we had before. We did consume some of our iron 3, because again, the iron 3 should be just yellow itself. So if we had just purely added iron 3 and nothing happened, then it should be more colorless. But again, right, adding the reactant drives the production of our forward rate. And so again, we saw it turn darker. So I'll say turn darker. So again, that means it shifted right towards the products. So does that make sense for the first one? So then let's look at the next one. And again, we'll reframe it in terms of reactants and products. And so this time it said add our potassium thiocyanate. And so the potassium doesn't really matter in this case. Again, what we're adding is our thiocyanate. So technically, we're adding our reactant, right? And so what did you notice when you added more thiocyanate? Did it go lighter? Did it go darker? So it went darker, right? And that's what we're expecting now from Le Chatelier's principle. That's what it's saying. So if we add more reactant, right now it's going to drive the production of more product. Okay, so we added reactant. So again, shifted right towards product. And then the next one you did, so this is a good one. So you added 3 molar HCl. So what was that doing though? And you can kind of tell me maybe what you observed if you're not sure. It does give you a hint in the lab manual what it's doing. But not necessarily reducing what, I mean, what do you, maybe reducing what, the concentration or?
Yeah.
Yeah, so it's reducing the concentration of what?
The iron molecules.
Exactly, right? So it tells us that it's going to react and make this iron 3 chloride species. And again, right, it gave us a little hint that it's going to remove the iron 3 plus. And so, okay, because it's taking it out of solution, creating something new, we can say, okay, it's removing my Fe3 plus, so my reactant. And so now if we're removing reactants, our equilibrium should shift to compensate that, right, and disassociate more of this blood red compound. And so is that what y'all observed, that it got lighter? Okay, excellent. So, right, so then it got lighter, which is again what we expect. And so now shifts toward reactants. So again, right, it's trying to make more iron 3 plus to compensate for adding that HCl, and that HCl taking the iron 3 plus out of solution. All right, so then the last one is kind of tricky. Well, it's tricky for 2 reasons, because A, it's hard to even see if it got lighter or darker. And then we have to think about what this means. So the last one said to heat in a water bath. And so now, first tell me, did it get lighter or darker? And then we'll figure out what that means. It got darker? I thought it was supposed to go lighter.
It was really hard to kind of look at that really see. But like the last one, it's like a little bit more brownish than orange compared to the first one.
Because it's supposed to go lighter. Like, so this is a hard one. So it should be lighter, so I'll give you that.
Okay.
Because it matters. And so what's supposed to happen, but yeah, I mean, I probably should have told you to pay more attention to that because it's really hard to tell comparing it with the standard. But it should go lighter, but then what is that telling us about the reaction? So we're trying to figure out if it's endothermic or exothermic, essentially. And so think about what that means. So if it's endothermic, that means that heat is a reactant. And then if it's exothermic, heat is a product. So then kind of based off of, well, again, based off of assuming that it went lighter now. So So now, is it endothermic or exothermic? What'd you say, sorry? Endo? So if it had been endothermic though, then it should be darker in the bath. So if it was endothermic, right, you're adding heat as a reactant. So if you're putting in the water bath, it'd be favorable. But like I said, it should have gone lighter since this is an exothermic reaction. So what we're saying, again, based off of these lighter results, is that this is an exothermic reaction. So it created heat as our product, right? So then once we heat it, well, that's not favorable to add more heat, so it's going to shift lighter kind of away from that. So that's what was supposed to happen. And again, just keep that straight in mind for endothermic and exothermic. So again, endothermic, right, you can think of heat as a part of your reactant. You need it for your reaction to go forward. Adding more heat, right, would drive it towards the product. Versus an exothermic reaction, if you heat it up, right, that stops it or slows it down. And then any other questions on the lab? I think the rest of the parts are more straightforward than the Le Chatelier's principle. So let's see, let's look at your homework and see if there's anything difficult there. So let's practice, I think it's 3 on page 2. I'll copy it over. So this is something that you'll have to do probably on your final exam. So this sort of idea of sketching an energy diagram, so it's on your homework. And so this one covers an endothermic reaction. It tells you your change in enthalpy, your activation energy, and it says to label all the axes. So go ahead and try that on your own if you haven't already. So I'll give people a few minutes to try it, and then we'll go over it together. Again, just looking at what a complete answer would be on your exam. So what do our graphs look like? What are some key points, especially with this being endothermic? So kind of what needs to happen. What do we do? So to me, that's like the key piece, right? That it's endothermic, and then it tells you your change in enthalpy. So then you kind of know how to set up at least 2 points, right? So what does that mean then if it's endothermic? Are my products higher or lower? Yeah, or the energy is higher. And so that's the first thing that I would do, so it doesn't matter too much. And then label your reactants. And then, right, so label your products here. And then, again, doesn't really matter how you draw it, just as long as you label here our change in enthalpy difference. So you want to label that, showing, okay, the difference from my reactants and products is the 10 kcal, again, endothermic, so products are higher. Okay, so that's, I mean, that's basically almost it, right? And then the last little bit is this activation energy piece. So we can just kind of put this, you know, somewhere. And then now kind of connect our graph and label this. So again, our EA is 30. So that's our reactants to our height here. And let's see, just, oh, and then let's label it. So it wanted us to label our transition state. So that's up here. So it looks like we have all our pieces, reactants, products, change in enthalpy, activation, energy, transition state there. Questions on it? And maybe think about, well, what would the difference be, right? Because I can only ask so many variations on an exam. So really, the only difference is let's compare. So what if it was exothermic? So, right, what if we had the same set of conditions, just exothermic? So again, think about how that would change. So the only difference would be our products would be lower, right? And we can sketch that out. So again, exothermic, if that had been the case, reactants, put our products lower. Label that change in enthalpy from reactions to products. Put our transition state again. Yeah, so this would be negative, but like I said, the way the question was worded, notice it just says the change, right? So that's what I'm trying to point out, that you have to look at this endothermic, and then you're just given the change in it. So, right, well, it depends. So, right, again, I'm not giving you the sign. So in that case, you have to look at the words endo versus exothermic, because the sign does matter, but if we're just calculating, right, so if we're just calculating the difference, then the sign matters. If you're given, like this word problem, it's not being explicit, because it wants to test you on the definition of exo and endothermic. So yeah, if it had said exothermic, again, just label it, same thing. So 30 now for our activation energy. And again, the only difference is the relationship of our products to our reactants there. Questions on that one? So we might as well look at your pre-lab. So let's just check your pre-lab, since, again, the Le Chatelier's principle, people can just get confused on that one. So again, I'll give people maybe a minute or two to kind of look at this, maybe look at it again if you already filled it in, and see if we can predict which way it will shift. That's good. This just blank. Okay, sorry, let me grab another VGA adapter. I don't know why this randomly turned out. Oh, are you kidding me? What's going on? That is super weird. Man. This is super awkward. I don't know why your class is going to start becoming like technology fail. That's really nothing happened. Oh, I don't know what's wrong. All right, let's just go over it verbally. And I apologize, I don't know why the adapter just failed. So what happens, what do we predict then if we add copper 2 plus to it? And it's kind of weird because I have right cloudy on the reactant side and then them disassociated on the product side. So what do we predict that adding more copper 2 plus will do? So cloudier to the left, excellent. So cloudier, left, and again, right, that's a little funny because it's just depending on how they write the equilibrium, where they put solid as a reactance. You know, I probably would have written it the other way had I been setting this up, you know, for myself, but we'll just follow how it's presented. Good, so then what happens if we remove hydroxide ions, so adding HCl? So right and clear, excellent. And so again, right, that was a little tricky. I really wish we had the display. But again, if it's removing your products from our right side, just by definition, then we expect more of our copper hydroxide to disassociate and compensate for that. And then the last one, so then if we're adding more NaOH, what do we expect to happen? So left and cloudier. So excellent. So again, in this case, we're adding product. So now it's going to shift back to the reactants and become cloudy. Excellent. So I had wanted to go over a quick combustion, oxidation, reduction problem. I guess I'll write it on the board. So looking at the combustion of methane, geez, everything. Look, my computer just came back. All right, so if we want to look at methane plus oxygen gives us CO2 and H2O. So let's ask, who's the oxidizing agent? So meaning it got reduced. So kind of think about how you would approach it first, and then we'll kind of go over it. And I'll write it on the notes. And I don't have it balanced, but it shouldn't matter for determining oxidation states. So let's look at it. And so what's our oxidation state? Let's start with oxygen initially. So what does it start off as? Remember, elemental form. So what do we say about things in their elemental form, right? What's its oxidation state? 0, right? So it starts off as 0. Okay, so that gives us a good starting point. And then we might as well do carbon as well. So if we kind of look at it, right, we have hydrogens. So they don't really change. I don't know if you want to put 1 plus over them, but again, they're not really involved. So then if hydrogen is 1 plus in our methane, what's carbon? Remember, it's neutral. And remember, carbon can formally be +4 and -4, typically. So then what's it in this case? -4. Excellent. Okay, so now this is starting to come together. And so now we can analyze our products. And so let me write this for the benefit of the notes online. And so then what's the oxidation state of oxygen then in our product? 2 or -2, right? So oxygen's always -2. And now what's carbon then, based off of that? +4. And so now we can tell what happened. And, I mean, you could have made a guess, too, just by this word, oxidizing agent. So you could have guessed it was oxygen. But now we can clearly see, okay, oxygen went from our 0 to -2 oxidation state, so it's gaining electrons. So we can tell that it was formally reduced. Remember, reduction is gaining, oxidation is losing electrons. Oil rig, and then we said if it was reduced, so it's our oxidizing agent there. And then of course we could say that carbon then was our reducing agent, so oxidizing agent O2, so that makes carbon our reducing formally, and then again hydrogen's just kind of there. So reducing agent, meaning it was oxidized, so carbon, right, lost electrons, and oxygen gained them. All right, any other kind of questions? That was like your quick redox lesson or recap.
How are you able to tell that the carbon can be -4 and +4 in this case?
I mean, we just went through that, right? So that's why the priority rules are there. So again, hydrogen usually takes the priority of +1. Carbon, I mean, part of why it has all those weird oxidation states is because we're not analyzing the structure. And so we just kind of have to base our carbon oxidation state mathematically off of everything else. And so sometimes with our organic molecules, again, without looking at the structure, we could get weird oxidation states for carbon, like half states. And that's fine because it's just an average. And then again, right, same thing with this carbon, we just base it off of oxygen. Again, oxygen is always just -2 priority unless it's a peroxide. All right, so I'll hand out the quiz at least. So probably just take your time on it. It's, obviously it's a little more math heavy since it's a little bit of balancing equations, a little bit of stoichiometry. So it's got a lot of little pieces on there. And some easy, some hard questions, and just read over it, take your time. If you need more paperwork, I can get more like scratch paper. And then of course, if you want to take a break, go ahead and take your 10-minute break, of course. I'm not sure what to do about this adapter situation. Anyways, I will stop the stream. Apologies for the mess at the end here.